Hi, I'm Aaron and welcome to my channel. Well, hopefully you're here because you saw my last episode, which was the history of the Apple I. I was blown away by the feedback. It was definitely my most viewed video by far, and I've only been doing this for, I don't know, 6 or 7 months, maybe 8 months now. So thank you for all of the support and the comments. I picked up I almost doubled the number of subscribers I have just with that one video. So I'm really glad people enjoyed it because it was a ton of work. But today we're not going to be talking about history anymore. We're actually going to be building the clone of the Apple I. So I've got my board ready. I've got my parts ready. I'm just about ready to get started. Just a heads up before I start though, this is going to be a little bit more technical episode. It's also going to be a longer episode. I'm going to try to go through step by step and especially concentrate on some of the places or the points in the build process where people can kind of stumble a little bit, maybe get caught with some things that they weren't aware of. So I'm going to be concentrating heavily on those gotcha procedures that you need to be aware of in order to make your build really, I won't say bulletproof, but as bulletproof as it can get when you're dealing with 1970s technology. So with that, feel free to skip around. I'll put the chapters in the description and you should see them on the timeline in YouTube. If you don't want to know how to fold a resistor properly and put it in the board, just skip over that part. It's not going to hurt my feelings in the slightest. So yeah, let's go back and work on some of these, some of the 70s technology and see if we can bring this Apple I to life. Speaking of which, there's something missing here. We're going to be dealing with a computer from 1976. This aesthetic doesn't quite fit. I know. Hey man, I can get down with this vibe. I think you're really going to dig this episode. So adjust your antennas, call your friends on the CB radios, because the Retro Hack Shack is starting now. Okay, well, it's that time. We're actually going to start building the Apple I clone. And yeah, it's exciting. It's so exciting. I've been a little bit afraid to start here. So what I have set out before me is the Apple I motherboard that I bought on eBay. I've got my Apple I operations manual. And over here on the screen, over there, you can't see it, is up on my screen. I've got Mike Willigall's build guide, and I've also got a bunch of tips from Uncle Bernie on the Apple Fritter forums. So I've done my research, I've got all those things, and I'm ready to get started. The other thing I have, of course, is the parts. In fact, you can see one of them here. It's an original Stancore transformer, and I'm going to be testing that later to make sure that this actually works. It's nice to have an original one. In fact, take a look at these colors. It's red, white, and blue. I mean, this was, remember, we're talking about 1975, 1976. That would have been right around the bicentennial for the United States. So I don't know if this is their original packaging, or maybe they did this for the bicentennial. I don't know, but it's very retro. The packaging on this box, even the lettering and stuff, is very much from the 70s, or at least from what I remember from my childhood. Anyway, I've got that there, and I'm going to be putting this board up a little bit like this because the lighting that I'm using is great for bench lighting. In fact, I've got a link to this on my tools section of the website. It's not so great for recording video because if I put this board up like this, you can see it reflects really well the light coming from the camera and plays tricks with light coming from the overhead light and plays tricks with the camera. So I've got some new lights on the way, thanks to my patrons. Thank you very much, patrons. You'll be seeing that soon, and I'm gonna get the whole reflection issue sorted out. Anyway, time to get going. The first thing we need to do is not put on any components. A lot of people might be tempted just to go at least like putting sockets on the board, right? You don't want to do that yet. You don't want to actually put anything on the board before you test the power rails. We want to test the power rails first to make sure that there's no shorts. So remember, some of the tips that I gave on the history video were to do your research, be careful of an open source board. I think I mentioned that. This one is probably built on the open source Gerbers that were released. And so because I'm not getting this from one of the official providers of these clone boards, I want to do some testing to make sure that it's working before I start putting components on. And I also said you need to test, test, test. And that is certainly true in this case. I want to make sure that there's no shorts to start out with, because once you start putting sockets, chips into place, even some of the smaller components like resistors, it can become difficult to troubleshoot what's going on the board. So the very first thing we want to do before we do anything else is actually test the power rails and make sure there's no shorts. Now, in the last video, I think I referred to the 6502 as a microcontroller at some point. I'm not sure. But anyway, someone in the comments pointed out that it should actually be called a microprocessor. And you can see here, it's written right on the board, microprocessor. I think dealing with Arduino so much, I think I just made a mental slip there. So a good place to test for shorts across the voltage rails is where these big capacitors are. So Mike Willigal points out in his build guide some great places to test, and it's going to be where these big capacitors are going to go in later. So for example, up here, this big capacitor is on the 5-volt rail. There's another one here, I believe, that's 5 volts. The difference is this is unregulated, this is regulated. Down here, there's the capacitors that go over the negative 12 and I think the positive 12 rails here. So we're going to test all these out, and it's nice because they're nice big pads you can easily identify. So I've got my meter in continuity mode, and I'm just going to go in and check to make sure that there's no shorts between these connections here. Yeah, so as expected, no shorts whatsoever. And just to show you that you know that my probes are actually working, they are. So if I was getting a short there, the meter would have told me right away that there was a short. So far, things are looking great. All right, well, I went through and tested as much as I feel comfortable with, and I don't see any problems on the board, at least from a connection standpoint. I went through and looked at some of the inaccuracies on the schematic, but I think it's all fine. I couldn't really find anything wrong. The next thing I want to do is I actually want to inspect all the traces on the board and the pads as well, and make sure that there aren't any stray components. I mean, you never know what kind of process this board was put through because it's not one of the more expensive boards. So I just want to take a close look at the connections and everything before I put components on. Now you can do that with a magnifying glass. You can do it with one of these. This is like a little, I guess it's like a Fresnel lens. It's flat, but it acts like a magnifying glass. It's kind of cool. So you could use something like this to look closely. Of course, you could use a microscope if you have one. I'm going to be using my trusty phone to do this. And luckily, I have a wide-angle lens that doubles as a macro lens. And so you can see when I'm zoomed in to about 4x on this lens, you can actually see really close detail. And so I'm just going to go over the entire board like this with my phone. I'm going to look at all the pads, like I said. See, here's a place where the solder mask has come up, it looks like, probably. Where is this? Right here. You can see how big my finger is there in the phone. But yeah, this will help you get a really good view of all the connections. You just want to make sure there's no bridges, that all the pads are intact. You know, just look for goofy things. There's a couple more places where either this got scratched in the mail. I wouldn't have actually been able to see this with the naked eye unless I looked really, really close. So this is actually really helpful for coming up with these some of these issues. If these traces were broken completely, then that could be an issue. In fact, I'm going to troubleshoot that trace right there because it looks like perhaps it may have been scraped away. And so while I'm zoomed in, any place like this that looks like it may have a defect or an issue that I want to investigate further, just going to take a quick picture and then I can come back later and take a look at it. And don't just do one side of the board. When you're done looking at one side, make sure you flip it over and look at the back side of the board as well. And in case you were wondering how to tell that this was not a real Apple I motherboard, you can see right down here in the corner, Apple I replica 2012 to 2016. So that's where the dead giveaway is. Because otherwise, you might not know, or a beginner somebody might be fooled, for example, on eBay, or somebody that didn't know that it wasn't real. Potentially someone could get swindled by somebody else trying to pull this off as an actual Apple One. At this point, you might be thinking about designing a replica PCB like the Apple One here, or something more modern like the RGB to HDMI module I sell on my website. Well, look no further than PCBWay, who are kind enough to sponsor this episode. You can get prototype PCBs as low as $5, and they do assembly, 3D printing, CNC milling, pretty much everything you need to build your projects. So check out PCBWay for low-cost PCBs and way more vintage computer fun. And I thank them for their support of the Retro Hack Shack. Okay, so with everything tested, now it's time to move into putting the resistors in. Now, if you are following along in Mike Willigall's book, he recommends putting in the sockets next, but I usually start with the smallest components height-wise off the board, and then move on to the taller components. So I like to start with resistors and diodes. So I'll be putting those in next. One other thing to point out about the board is that the board itself, like a lot of boards of this era, were built with a legend or a grid system that you could use to identify components. So you'll see this a lot. Even if it wasn't on the board, you'll see it, like, for example, in service manuals or Sam's computer facts. You'll see that they've put in their own legend so that you can find where the components are. In this case, it's right on the board. So we've got A, B, C, and D corresponding to where the ICs go in from the top of the board. And then along the bottom here, we have 1 through 18. So with this grid, you can easily see where to put things. So for example, in the build guide, it says to put a 3000 or 3K ohm resistor in location A5. So you look for A, you go over to look for location 5, and somewhere in this area would be a 3K resistor, and here it is right here. It also says to put 3 3K resistors in location A8. So again, here's A, look for 8 along the bottom here and go up. There's 3 3K resistors right there. Now, it's pretty easy though, even without that grid system, these are all labeled. So these are all 3K. There's other resistors up here that are 7.5K, for example. So it's fairly obvious if you've built these kind of systems before or worked on these kind of systems where things go. But if there's ever any doubt, you can go ahead and look up by the grid where these components are going to go. Now, I'm just going to be using standard modern resistors for this build. If you really want to be authentic, you can go with the old school kind of brown looking resistors for sure. They're not too expensive, although they'll be more expensive than these, whatever these are, like, tenth of a penny or something for these resistors. But in any case, I'm just going to be using the normal ones. This is an area where I'm breaking with the vintage look of this system because, I could always go in and replace those later if I really, really wanted to. I'm not too particular about the resistors. When I'm putting resistors in a board, normally I just take the resistor and, bend it however I want and just kind of shove it in the holes. And, it kind of works itself out, but then you end up with resistors that are kind of haphazard and stuff. So for this project, because it's more of a showpiece than, just something some kit I'm working on or some project I'm working on or something like that, I want to be a little bit more careful. So I'm trying one of these, bendy tools. I don't know what they're called, but they're for spacing, resistors, and I suppose other components as well in your board to make sure that they're bent to the correct sizes. So I'm just going to put the resistor in here and bend it so that it is nice and square. With any luck, that should just go right in the holes, aka pads. Yep, it does, and it lays nice and flat, and it'll look good to have those all nice and even instead of maybe up and down and backwards and things. So that's how I'm doing the resistors. Okay, so I've soldered in the resistors, and I went ahead and did these radial electrolytic caps because those won't get in the way either. But I did want to point something out. I actually put in some resistors over here, and then I realized I had made a mistake and took them out. So this 74123, you can see there's supposed to be a 27K and a 10K resistor as well as a couple capacitors on either side, and this is done for timing reasons. Now the issue is that depending on the 74-123 and the capacitors you use, definitely the resistors will probably need to be different to make this work, and if they're off a little bit, the timing can go bonkers and you could end up with a non-working system. So this is one of the reasons why I went ahead and bought some of the chips from Uncle Bernie, is because he actually tests this and provides the right resistor values to match the capacitors in the 74-123 that he sends. He actually tests that to make sure it works first. And then when he sends it to you, you've got basically a matching set for this one socket. This is why I took those resistors back out. And when I get around to putting the actual chips in, and after I put the sockets in, I'll come back and make sure that I use those components he supplied to avoid that problem. Now it's time to go ahead and put in the next highest thing on the board, and that would be all of these sockets. That's going to take a while. Alright, so I just finished soldering on my last socket. Let's turn it over and see how it looks. Hey, not bad. It's actually starting to look like a real computer with all these sockets in here. One thing to point out is that all these vertical sockets actually face the bottom of the board, not the top, as you might expect. So keep that in mind when you're putting the sockets in place. So with all the sockets in place, it's now time to solder in the decoupling capacitors and the other ceramic capacitors that are on the board. There's quite a few of them around, and you'll notice that on the board, a lot of them are labeled 1.0, which typically, if you were to read this, would signify 1 microfarad or maybe 1 nanofarad. But in this case, most of the boards, the Apple I boards, were actually, wherever there was a 1.0 ceramic capacitor called for, they were actually calling for 0.1 microfarad and not 1.0 microfarad, so 100 nanofarad. So that's what I'm going to be putting in here. I don't know if that was just incorrectly labeled or what, but just keep it in mind. If you're just looking at the board and not following a build guide, you might be tempted to put 1 microfarad capacitors in there. Actually, you're going to need to put in 0.1 microfarad capacitors wherever you see 1.0. The rest of the board is labeled correctly. So for the other ones, they're fine, but just all of these that say 1.0 use 100 nanofarad or 0.1 microfarad ceramic capacitors. Okay, so all the ceramic capacitors are in the correct place. I've also soldered in the crystal and the transistor at this point. Notice I haven't put any of the big caps or the big power regulator here yet, and that's because we need to do something else first. In order to make it a little bit easier, we need to add some reliability mods. And the reason I'm doing this first is because if I had those big caps in the power regulator here, it would be hard to set this down on a table or propped up like I have it here in order to do these mods. Now, the reliability mods consist essentially of a bunch of bypass capacitors that can be added to the back of the board, or if you're clever enough, you can actually add these hidden beneath the sockets themselves. I chose to put mine on the back of the board, and you can find this information on the Apple Fritter forums. If you order an IC kit from Uncle Bernie, he includes these capacitors for you, but they're easily sourced elsewhere. To install these mods, you just follow along with the diagram I showed earlier, cutting the components to scale and then soldering them where they need to go. Doing these mods should make it much more likely that your Apple I will boot up the first time you turn it on. The other thing to keep in mind is it's important, especially with areas where you have a lot of connections close together, that you don't end up bridging pins where, on the back side of this board. So what I did was I took my phone, after I was all done, I took my phone and I went in and took a look at all of these connections, and I also tested them with my multimeter to make sure that I wasn't bridging any of these pins, because it's really easy to do that when you're adding components to the back of these boards. Okay, so we've come to the time when we can start adding some of these power components. I've got my power transistors here, but these are new old stock power regulators, rather. And so I want to make sure I test them before I put them in to avoid any issues up front. So what I'm doing is I've got the positive and ground, the input and ground connected to my benchtop power supply, and then the output pin is over here. What I'm going to do is test that with my meter to make sure that I'm getting the expected output from these transistors before I put them in the board. Okay, so I'm feeding in 20 volts. And let's see what I get out. I should be getting out of this one. I think this is negative 12, but I covered up the reading. Be careful not to short this when you go in to do your testing. Okay, so this is, I'm getting 14.93 volts out. So this is a positive 12 volt regulator. And it looks like this voltage regulator is bad. It's reading negative 0.8 volts. Okay, so I believe this should be a negative 12 volt regulator. So let's just check it and see carefully. Nope, this is a 5 volt regulator. I'm getting 5.5 volts out. Okay, well, I just made a silly mistake because I forgot that on the LM320s, which are the negative voltage regulators, the pins are switched around. So instead of the input being on the far left, the input's in the middle. And so it's ground that's on the far left. So now if I measure between the far left and the far right pins with the power applied, I should get a negative voltage. So let's just test this again. Turned on the voltage, 18 volts in. And if I test between the far left and the far right, now I'm getting negative 5 volts. Yay! That was silly. Okay, I've gone ahead and soldered the 3 voltage regulators in. We still have to do this big one over here. But these voltage regulators, keep in mind 2 things. Number 1, this is your last chance to check the rails and have them be completely disconnected. So if you want to check again where these big capacitors are going to go, for example, for the various voltage rails, and make sure that you don't have any shorts, now's the time to do it. Once these go in, or as you're putting these in, also keep in mind that the voltage regulators go in differently. They don't all go the same direction. So the one down here, which I believe is the positive 12 volt regulator, goes in with the front facing this way and the heatsink part facing that way. Let me turn this so you can see it a little bit better. And then the 2 back here, the negative 5 and negative 12, actually go in the other way. So the heatsink is facing this way and the front is facing that way. So just keep that in mind when you're putting these in. Check the build guide and make sure you have those oriented correctly. All right, just a few parts left now to assemble the plus 5 volt voltage regulator is here, and that's going to go in. I put just a tiny bit of thermal compound on here to make sure that the heat transfers into the heatsink. That is going to go on like this. These regulators, the pins are offset to one side, so it's hard to get this in backwards. But basically all you need to do is line up the heatsink with the holes. If you were to turn it around, it wouldn't line up correctly. So you just line this up with the holes in the board, and you can put your 5 volt regulator in. Make sure that you screw down the regulator to the board here using some screws and a nut. And then you can solder in the leads to the back of the board. So that's the 5 volt plus 5 volt regulator. I'm also going to go ahead and put these big Sprague or Sprague caps in, and I made a classic mistake here. I trusted the eBay seller I got this from to provide the right ones. These are actually slightly larger than the holes where they go. The other one will fit fine. This one will fit fine right here, and it's a little bit smaller than the width of the pads here. But these, the 2400 microfarad that I have, are actually a little bit bigger. So it's going to make it a little ugly. It'll still work. I can still get it in there, but I may come back later and change these for slightly shorter Sprague capacitors to make it look a little bit nicer. And the only other thing left to do is to put in the video level adjustment pot. After that, I think we're ready to test the power. Now the power connector uses one of these 6-pin kind of old school power connectors, and the video connector uses a similar one, but it's only 4 pins. So since I don't have a 4-pin one, you can certainly get those. I'm just going to take an extra 6-pin connector and just snip off 2 of the pins. If I can do this cleanly, it should make a fine connection and shouldn't be a problem. And then I'll also snip off the corresponding socket as well. Now, before I hook up power, I do want to clean off the back of the board, get all that flux residue off from all that soldering. So I took the board into the kitchen and sprayed it liberally with a lot of 91% IPA, and then scrubbed everything with a brush and gave it a good rinse in the sink. All right, well, I've got the back of this board all cleaned up, and it's looking really nice now. I don't know if you can see how shiny that is or not. But it's looking nice now. But just to note, I had to go over this 3 times with a stiff brush. In fact, it was this brush right here, kind of a toothbrush, anti-static brush with looked kind of like a toothbrush. And I had to go over it 3 times because the residue on here was not coming off very well. And so I think it's a good lesson. A lot of times you'll see YouTube videos like mine where, well, we spray a little alcohol on there, rub it off, and we don't do anything else. Actually, that can leave a lot of flux residue on there. You just kind of spread it around. And so it's important to, do a thorough job, get the residue off there. For small jobs, you can just spray a little IPA on there, loosen it up, and then use a Q-tip or something to remove the residue. For big jobs like this, like I said, it took me 3 times to get all the residue off. Now the board is really nice and clean. So, and don't be afraid to wash it off. I washed mine off afterwards. I took it out to the garage, used compressed air to spray all the water off both sides of the board, and especially getting underneath all these sockets to make sure that I got all the water out. So this is pretty much dry, but just in case there's any additional water underneath any of the components, I'm going to go ahead and let this dry a little bit more while we move on to the next item that we need to build. And that item is the ACI, or Apple One Cassette interface. We need to build this board so that we can get programs on and off of the computer. So taking a closer look at this board, you can see that it's not marked up nearly as much as the main board for the Apple One. So you have to pay a little closer attention here, although you can kind of figure out what's going on. There's these columns across the top, 1 through 6. And so you know that components go in here. Like this will be a for an IC, and then more ICs will be populated here. And then up here you have some components, some resistors, more resistors across the top here, and then 1 capacitor right there. Now that capacitor, according to Mike Willigal, he also has a build guide for the Apple cassette interface, but that capacitor there can be increased from the recommended 0.01 microfarad to 0.1 microfarad, and he claims that that actually increases the reliability of this board. So I'm going to be doing that. Just be aware that in the original Apple documentation, they recommend putting in a 0.01 microfarad capacitor, ceramic capacitor there. So I'll be replacing that. Otherwise, like the other board, we're going to start by making sure that this board that I bought on eBay is actually, first of all, doesn't have any shorts. So put the meter in continuity mode, and there's some good places to check according to Mike on this. And if I remember correctly, they are here over in this corner. When you turn the board over, this fat trace here is actually ground. This last pin here on the board, or this last connection here on the board, is actually 12 volts, and then you have 5 volts here where this little via is, and there should be no connection between any of those. So you can simply go through and just check each of those and make sure that there's no connection like that. So I'm not getting any continuity between these, and that's what you want. You don't want any connectivity at all between those power rails. Other than that, I'm going to use the same process that I did with the main board. Start with the small stuff first, or the shortest stuff on the board. So that'll be resistors. Then I'll put in the sockets, followed by the capacitor up here. So I'm just soldering in the components here, and I got to say, I love the colors on these transistors. I guess I didn't realize there was transistor color codes. I think I got these new old stock. This is very 70s looking to me. It reminds me of stuff from my childhood. So I don't know. I just thought it was cool, these color codes. I guess I didn't realize there's color codes for transistors, but that's pretty neat. All right, well, here is the Apple I cassette interface, and I went ahead and put in the ICs as well since I had them available. Not too worried about putting these in just yet. I'm just going to be careful where I set it to make sure I avoid any kind of static discharge or anything, but it's a pretty simple board. It should be fine just like this. I am going to check one more time to see. I should have like around a 9.5K resistance here. Between 5 volts and ground. So let's just check that real quick. Okay, yep, 9.5 exactly. So that's good. And then I did want to talk about these audio connectors. So these are the original audio connectors that would have been used with this board when it came out back in 1976. I went ahead and bought some authentic ones. The way this works is you just unscrew this little screw. You pop them through, and then screw the screw in from the front. And then on the back, there's a couple of small pads here, and these attach to the tip, the part that connects with the tip of the plug when you put it in. And so I'm just going to solder a little wire to this post right here. And I've tested this with the multimeter to make sure. And it's best to do this when you actually insert a plug. Let's see if I can get this to focus here, because there's also a switch right here. And so to avoid confusion, it's best to go ahead and insert a plug, which will press this down and open the switch. And then you can use your multimeter to figure out which one of these other connections is the one that goes to this tip connection. And by doing that, you'll know where to solder a little piece of wire just right here from here. In this case, it's this connection on the side. I'll just put a little wire from that pad over to this, and this board will be good to go. All right, well, it's finally time to start working on the power supply, and then we can test the power connected to the board here. But I've got to open up these original Stancor transformers first. The big one, of course, is the big 3 amp Jobby, 5 volt, 3 amps. And then the smaller one here is, I believe, a 28 volt, 1 amp transformer. And these were the original ones that were recommended to use in the Apple manual. So I felt very lucky that I was able to get these. You've probably seen them in the background here all throughout the videos. I used them to prop up my board as I was working on soldering things, knowing that I was going to have to open these up eventually. But yeah, I know I said it before. I just love these colors. Totally 1976 bicentennial. For the United States, red, white, and blue. I'm sure there was all kinds of products that were red, white, and blue. Maybe Essex Stancor transformers were always had this red, white, and blue, but I wouldn't be surprised if this was just for the bicentennial. Anyway, let's go ahead and open up the big one and take a look and see what it looks like. Wrapped up nice and neat. There it is. New old stock. Just exactly as it would have been as part of as part of an original Apple I. Wow. Now the paper here is a little bit crinkly, but it's not too bad. Transformers are typically pretty reliable, so this should work. We'll find out, of course, when we hook it up, but this should work just fine. Transformers typically don't go bad. Usually your power transistors or other things will blow. A fuse will blow, hopefully if you have a fuse, which we will, before the transistor goes bad. So that is just awesome to have an authentic power supply like that. Okay, let's take a look at this other one. Again, we're taking a risk here, right? Because we're using these, even if it's new old stock, we're using these parts that have been sitting around. I mean, who knows? They could have been underwater. This one definitely looks like it's never been opened. Let's see. Wow, all the power supply fanboys, or the transformer fanboys, are going wild here. You can see the Stancor manual for the transformer underneath. And here's the stand core transformer for the 28 volt line. Very big, very much overkill these days. But here is the original service manual that went with the this other stand core. That's pretty cool. That's pretty neat. Well, I went ahead and got this board to mount these on and some screws to kind of hold it down. I wanted something, number one, these are pretty heavy, and I wanted something just temporarily to be able to move this out of the way, keep the mains power kind of, everything kind of on this board as much as possible. Hello, Penny. Hello, are you saying hello? Yeah, are you saying hello? You can see Penny's nose here. Come here, Penny. Do you want to say hi? Hello, Penny. Hello, Penny. You want that paper, huh? You want that paper? You're being really good. Can you shake? Where's your shake? Where's your shake? Can you shake? Oh, good girl. Good girl, Penny. Okay, hopefully Penny doesn't get up here and get any of these parts. There is a schematic, by the way, in the manual for how to do these. We'll see. The best thing, if this was a little longer, it'd be nice to mount it like this, with the black wires going out one direction, because those are where the mains come in. Maybe I can do that. I think I've got enough room to stagger it here. And then the rest of these wires, I will connect directly to the plug that's going to go in the Apple II, or Apple I. What am I talking about? Now I've got a fuse as well. So this will go in between the mains. I'm going to have to beef up this wire just a little bit. This will go on the main side. I've got a 2 amp fuse in here now, even though this is 3 amp. We should not get up to 3 amps being drawn from this for right now. I may replace this with a 3 amp fuse later on, but I don't think we're going to exceed that now for our testing. So I've got a 2 amp fuse here, which we will put in line. And then a little switch just to help out, make things a little bit easier to turn things on and off. What you got, Penny? A plastic bottle, of course. Yeah, so just to make sure we don't overdo things here, I'll put in the fuse. And then later, when I actually have this in a case, a replica case, I'll mount the fuse holder to the side of the case. And of course the switch will be mounted on the side of the case. So this will all be buttoned up nice and neat. If you're playing with mains power like I'm about to be, make sure you know what you're doing. I'm going to be wrapping all of the wire at least in electrical tape just to make sure that everything's safe, because this is going to be sitting on the desk at least for while I'm doing testing, and I want to make sure we're safe. Now to plug this into the wall, I'm just going to be hacking up one of these IEC type cables. And I've got so many of these things, it's unbelievable. So I'm just going to hack the end off this, and this will be the cord that goes over to the mains. All right, well, it's time to do a test. I have everything hooked up, taped off, so no wires are exposed here. I'm going to be testing the 10 volt, 3 amp supply transformer first, see if I get somewhere near 10 volts. It should be something north of 10 volts. And then I've taped off all the other connections on the other one, and I'll test the 28 volt one transformer next. So let's go ahead and plug it in, see if we get any smoke, anything happens. Let's see. Let's go ahead and turn it on. Okay, 11.53 volts. That's perfect. That's exactly what I'd expect to see. Okay, I've got this one hooked up. Let's test the 28 volt transformer. All right, we're getting 33 volts AC, which is what you would expect on an AC transformer, to see a voltage that's slightly higher under no load from a 28 volt or from a transformer like this. So these are looking really good. Now, of course, there's no load on them. They could go haywire when we start adding some load, but I doubt it. I think these transformers are going to be just fine, even though they are 45 years old this year. All right, well, I've managed to get these wires crimped, but one thing to keep in mind with these older, if you're going to go with these original transformers, the casing on the wires is a lot thicker than it is in newer style or more modern transformers. And so you're crimping, you may have to be careful with the way that you crimp this, because it's difficult to get these pins actually around the casing. The wire is much smaller ratio to the casing on here. And so just be really careful with your crimp tool. I basically had to push the casing in, close the top a little bit with my needle nose pliers, you know, kind of close it around there, make sure it was in there all the way, and then take my crimp tool, crimp it, and hopefully I've made a good connection with the wire here. I'll find out once I put it on the board. The first thing I'll do is test this unregulated AC voltage again, make sure that's coming through on the board, because if this isn't crimped all the way around the wire, of course, you're going to have a bad connection there. The other thing is to make sure you reference the schematic in the manual so you know which way these go in. They're not numbered in order. They kind of skip around a little bit. So just make sure you follow the numbering on the motherboard itself, and take a look at the schematic and make sure you put these in the right direction. Otherwise, you know, you could have a very bad bad time with it if you don't put them in the right way. Okay, my connector's plugged in. This will be the first big test of the power to see if anything blows up. I'm going to be testing to see if I'm getting the various voltages. And the best place to do that is around these kind of medium-sized caps here. We should be able to test all the voltages around there. I'm also going to make sure that these aren't getting too hot, the power regulators themselves. If they're getting really hot at this point, remember there's no chips, so there shouldn't be very much drawing, or hardly any load at all. And so if these regulators are getting pretty warm, that means there must be a short. But I've tested for shorts. I don't think they're shorts. But you never know. At this point, it's always interesting to see what's going to happen. So let's go ahead and plug in the power and turn it on and see what happens. Turning on the power. Power's on. Don't see any smoke. Well, just to make sure, I'm going to test the DRAM sockets, because the DRAM should have all of the voltages on it. So pin 16 should be ground, and pin 1 should be -5 volts, I think. Let's see. Yep, -5 volts. That looks good. Let's see. Pin 8, I think, should be +12. Yep, +12. 9 should be +5. And there's the +5. Okay, it looks like pin 1 over here on the 2513 character generator should be -12. So let's see if we can find that. Hey, look at that, -12. Perfect. So now I know all the voltages, all the voltage rails are working properly. Nothing's getting too hot. Be careful sticking your fingers down in here. I'm being very careful just to check the regulators. Nothing's hot. Nothing's getting shorted. Everything looks great at this point. So, fingers crossed. See where we go from here. Okay, so now I'm going to go ahead and start finally populating the sockets. The thing you probably wanted to do first is actually one of the last things we're going to do. Now, I actually bought some ICs that are pre-tested from Uncle Bernie. And he's been kind enough to send these to me. They're all wrapped up in tinfoil here. But they're broken out by row. So I've got row A, row B, C, D, and my ACI chips, which I actually have 2 sets of these anyway. So if the ACI doesn't work, I have some spare chips to use. So what I'm going to do is I'm going to start populating all the chips, because I know that these are already tested. So you might have noticed, for example, in 8-Bit Guy's video that he did when he was doing his build, he tested the video portion first and then tested the computer portion. That's fine. You can do that. But the reason you do that is because it, reduces the number of chips that could be bad by half. So in this case, I'm pretty confident that all these chips are going to be good. So I just need to be careful when I put these in that I don't bend any IC legs when I put them in the socket. That's going to be my big concern here. The other thing is there's some components over here I left out on purpose. And that is because they are pre-tested, pre-configured resistors and capacitors that Uncle Bernie tested to make sure the timing was correct for this 74123 chip. So I think if I open up this row B set of ICs, yep, sure enough, oh, here's a little note. So here's row B, and he's got a little post-it note here that says for the 22K, put in this 27K, or sorry, put a 22K in the 27K and put a 13K in the 10K. And then he's got a spare as a spare one as well. And then he also sent, where are they? He also sent these timing capacitors that he tested with the kit. So I'm going to go ahead and solder those in now and then start filling up all of these sockets. There it is. All the ICs are in their sockets. As I was going through, if I heard anything that didn't sound like it was going in right, I went ahead and pulled it just to make sure that there weren't any bent pins. But all the ICs are in except for these two. If you were noticing carefully, these two are actually out. And that's because these are the PROMs which have Wasmon on them, which helps the computer get up and running. These have a special firmware loaded on them in addition to Wasmon. These, I think, I may get this wrong, but I believe these are 512K PROMs versus the originals, which were 256. They have a little extra space on them, and Bernie has programmed a test program that you can use to diagnose and make sure the memory's working and things are working okay. And the way that you enable that is you just bend out one of the legs on each of these PROMs. It's pin 14. You just bend that out a little bit, being careful because you don't want to save that for later. You don't want to bend it too many times, otherwise you'll break the pin off. But if I bend out pin 14 on each of these and then put them in with pin 14 missing, it'll start up his magic memory tester and burn-in program that will run. So I'm going to go ahead and configure those that way. And then when we test this up, hopefully if it boots up, we'll see Bernie's program running. All right, so at this point, all the chips are in. There's only one last thing to do, and that is to short some of the jumpers on the board. There's actually several jumpers here. There's two that say 6502 down here. There's a no DMA one that you have to short. And then there's a few more up here. So you can see here the ones on either end. There's one that says Y, and just below it says F. You have to short that. And then there's one over here that says X and 0. You need to short that. And then if you have this memory bank populated, the W bank populated, which you probably do, you need to run a jumper from W over to E. And then you need to jumper Z to D. And that should be all the jumpers, I hope, that I need to set. So I think I'm ready to try this out. I was looking for a small monitor that I could have in front of me to make sure that it was actually coming up on a real monitor, because that's more reliable than just looking at my video capture. And I thought, why not use the Apple IIc monochrome monitor? Because it's a perfect composite monitor made by Apple for the Apple IIc. So that just seems like a perfect addition to actually test this out. I've got it powered up. I can see the green light, so hopefully I've still got my settings correct and I'll be able to see what's going on. So here we go. This is really the culmination of months and months of work here. I just hope nothing goes wrong. But if it does, I guess I'll capture it on video. My hands are shaking. Okay, let's see if we actually get anything coming up on the screen. Here we go. Power's on. Okay, I'm not seeing anything. So I started to test all the voltage rails when suddenly I looked over at the power connector and I noticed that one of the wires had actually popped out of its crimp. I guess I didn't tighten this one down all the way. All right, well, the power cable is, I think, recrimped and fixed. It seems tight. None of the other connections are coming out, so fingers crossed this time. After that scare, we'll get something to work here. Okay, let's go ahead and try it out. Okay, I guess I gotta cross my fingers and my toes this time and hope it works. Come on. Here we go. Oh, I've got blinking @ signs. It's actually working. This is actually working. Okay, here we go. Okay, this is awesome. This is so cool. The capture card's not very happy, but it's actually working on this screen. So I wonder if I could change the video level adjustment and make the capture card happy. Let's see. There we go. I think I can see it over there on the capture card. So there we go. It's actually working. 5-volt regulator is getting warm, which it should. So yeah, this is pretty cool. I'm going to try to reset it, do a reset. You have to short out pin 12 on the keyboard socket to 5 volts, and then the screen should become clear. So let's do that. Okay, there we go. Blinking @ sign, and then I think I can do a reset, right? Short pin 1 of the keyboard to any nearby ground, pin 9 of the keyboard connector. Okay, so let's see. Pin 1 of the keyboard connector to pin 9 of the keyboard connector. Hey, look at that. I'm actually getting ASCII. Awesome. That's so cool. I think this is working because this is Uncle Bernie's. Ooh, those proms are kind of warm. I'm getting Uncle Bernie's test program here that's reading and writing from memory, I believe. That is so cool. Well, I cannot believe that this is actually working. Almost first time. Almost. All that work and headache trying to get this thing to work. Man, that 5-volt regulator is hot. I'm definitely going to check out. 5-volt regulators definitely do get hot. 7461s are really hot. All right, well, it's working. I'm going to go ahead and turn it off, and then I'll troubleshoot some of these issues and see if I need to fix anything else on the board. But this is a really, really good sign. Okay, so I've been doing a little bit of experimentation and checking the temperatures of the various chips on the board and the regulators as well. I just want to make sure they're not too hot and nothing's going to burn up and fail from getting too hot on me. One of the things I found is that the chips can vary quite a bit in heat output based on the series of TTL chips they are. For example, the original TTL chips, let's just pick one up here. This is a 47161. So the 47161 gets pretty hot, but I also have in here a 41S161, which is the Schottky version of that particular logic chip. That one gets quite a bit hotter than the original 47161. And I also dug out some LS series logic chips and put those in. And what I found is that the LS chips are the coolest, but there's no guarantee they'll work in a setup like this. They happen to work because I'm running, so they're working here. But the LS chips run the coolest, and then the oldest TTL, original TTL chips run the next hottest, and these Schottky ones run really hot. So what I did was I actually sat down and created a spreadsheet and took temperature readings with one of these laser temperature reading sensors. And I've got temperature readings for every single chip on the board because I couldn't find this anywhere online. 44.8, 38.
Okay.
31.8. So I've got those in a spreadsheet. I'll make those available. I can put a link in the description for you to download that. But basically, it looks like everything is running okay from a temperature perspective. And I've had this running for several hours and haven't noticed any problems. The temperature of the chips will rise to a certain point and then stabilize there. The other two things that get really hot, or at least in my case get really hot, are the proms over here. So those get really hot. I think they were around 50 degrees Celsius. So, I can leave my fingers on there for, maybe 2 or 3 seconds, and then I want to take them off. And of course, the thing that runs the hottest, and this is normal, is this big 5-volt regulator over here, the LM323K. That actually runs about 80 degrees Celsius. So really hot, but that's normal. But it's also why you don't want to enclose this too much in an enclosed area, because that will continue to heat. If you were to really close off your case around the board, that could be an issue. But even just cupping my hand over that regulator, that could warm you up on a cold day pretty well, actually. So yeah, just be careful of those regulators. Be careful what's around them, what's touching them. You definitely don't want to start a fire, and you want to make sure there's some airflow. And it really speaks to the old systems and why they were so power hungry and how far we've come with switching power supplies and the like that don't take nearly as much energy to transfer. The efficiency is so much better these days. So yeah, I'll make that spreadsheet available if you're curious what the temperatures, at least in my case, look like. I can't say that they're always going to be typical, but at least you'll have, if you're building one of these, you'll have a guide to know, hey, this one seems like it's way out of whack, and maybe that will start your wheels turning as to what might be causing a problem. Okay, now I think we can take this out of test mode and see if we get to the normal prompt. And to do that, I'm just going to bend the pins on the proms that I pulled out. I'm going to put those back where they should be and reinsert these proms. Okay, the proms are back in, and I'm ready to adjust my video output. Hopefully I can get this on the capture card. Let's turn it on, see what happens. Okay, well, good. We've got the flashing screen here. Let's see if we can reset. Hopefully we'll get to a prompt, but this is a good sign. Clear screen. We've got a blinking @ symbol. Capture card definitely doesn't like this. Let's try hitting the reset. All right, there we go. Got a prompt. So the backslash, I believe, is the normal prompt that you should see. So I know it seems anticlimactic, but we've got that backslash, and that is really good progress. So really glad to see all of the chips seem to be working. No issues so far. Got the backslash. Everything seems to pass all the tests that I've done. So all this effort so far is paying off. Well, I've got to tell you, I was so happy to see the Apple One come to life when I flicked that switch after that little hiccup with the power connections. That was the moment I had been dreading because I had sunk so much time, effort, and money into this project. I would have been pretty disappointed if I had to stop there and do a lot of serious troubleshooting. But some of the things that saved me from doing that were buying a kit online that had been tested ahead of time and then following those procedures that I outlined in the episode step by step, lots of testing, and that culminated with the Apple One actually working at this point. Now, for the next episode, I'm going to be loading some programs on the Apple One. I'll build a case for the Apple One. We'll connect the keyboard. I guess we should do that first before I start loading in programs. That's probably a good idea. And then I'll have a monitor, a period monitor that should work with the Apple One better than this monitor that came with the Apple IIc. So that's coming up next time. If you want to see more of these episodes, check out my Patreon page and become a patron. So I'm going to start doing after episode commentaries for patrons only. So after this, the credits roll on this episode, I'll come back on and have a few thoughts about the episode and let you know some of the behind the scenes work that went into doing the episode and building the Apple One, for example. If you want to see that kind of content, just sign up on my patron page. For I think it's $2 or more, you'll be able to get that kind of content and also ad-free content. And I hope you join and support the channel. Or you can always follow me on Twitter or Instagram, where I post things in between episodes. With that, thanks to everybody. Hello to all my new subscribers. I hope you enjoy the content in the future, and let me know in the comments what you'd like to see more of. I'd really appreciate it. Until next time, thanks for watching. If you want to support me on Patreon, you can go to patreon.com/retrohackshack and sign up